Tonight, the sky offers a startling sentence. The interstellar comet people are calling Three-Eye Atlas has turned green. No preamble, no whisper. A pulse of color at the head, where gas and dust bloom from a nucleus older than our sun. Telescopes across the night pivot. Amateur rigs hum. Observatory consoles blink alive. Frames pour in now. The narrator is not the hero here. The evidence is. The color appears in the coma, not the tail. It hangs like a lantern over a grain of ice and rock that fell between stars for uncounted ages. If this green holds, it is not a mood. It is chemistry. It is origin. We begin with restraint. First question, is the green in the sky or in the camera? Second, is it transient, a one-night bloom or a stable signature? Third, if it is real, what molecules sing that note and at what energy? Half the room leans forward, the other half leans back. Someone whispers caution, another whispers opportunity. What if the green is the first honest sentence this visitor has spoken to us? Method, not mania. Multiple filters, comparative exposures, calibration stars, spectra that slice light into lines we can test, confirm, repeat. Light curves over hours, then days. Independent teams, shared protocols, a chain of custody for photons. We will not promise answers. We will promise the hunt. Tonight gives us a claim. The next nights will try to break it. If the green survives, it could unlock a door few comets have ever opened for us. Which door? In astronomy, turned green is not a mood or a metaphor. It is a measurement. It means the light from the comet's head, the haze called the coma, shows an excess in the green part of the spectrum relative to blue and red, and that excess repeats across frames and instruments checked by independent observing groups. The location matters. The green appears close around the nucleus, not down the long tail. Viewers confuse the two because long exposures smear light into a plume, and brains prefer one object with one color. Eyes and cameras do not tell the same story. In the dark, the human eye leans towards shades of gray. A camera stacks seconds, boosts faint signal, and applies white balance that can tilt the palette. Processing nudges color. Filters matter too. Broadband red, green, blue often weights the green channel. Narrowband filters target specific emissions and force a harder test. Comparison stars anchor reality. The likely physics has a name, the Swan bands of diatomic carbon. They cluster near 4,770 angstroms, 5,165 angstroms, and 5,635 angstroms. When excited by sunlight, they glow green. Cyanogen plays a side role. Its strongest band sits near 3,880 angstroms, mostly in ultraviolet. It can pump energy that cascades into green, even if eyes never see ultraviolet directly. Why not the tail? Diatomic carbon breaks quickly, and tail physics sorts gas and dust by forces and lifetime. Dust and ion tails carry other colors. Beware traps, sensor saturation, sky gradients, air glow, urban light, even aurora. The cure is calibration frames, reference stars, and replication across nights and teams. One night, two filters can confirm or kill the claim. Are we ready to try? Discovery began on the 1st of July 2025, when the Atlas survey in Chile flagged a soft point sliding through morning frames. The sky was steady, the moon absent, and early stacks showed a compact coma plus motion that did not match near-Earth traffic. The trail was faint but consistent across detectors worldwide. The first notices traveled fast. Observers fed coordinates to mounts and returned positions. A provisional path was posted. Teams extended the arc through the night and into the next. With each measurement, the fit hardened, and the label edged toward a bolder phrase, Interstellar Visitor. The numbers told a simple, heavy story. The eccentricity cleared the wall of one. The orbit was not bound. Excess speed at infinity refused to vanish. Geometry added texture. The path cut steeply across the ecliptic, approaching from above the sun's equator. That tilt narrowed evening and morning windows but lifted the comet above the worst murk. Classifying it as interstellar demanded caution. Analysts worked in the barycentric frame and tested solutions with and without small non-gravitational pushes from outgassing. Even after those terms, the curve stayed hyperbolic. Perihelion would arrive in late October 2025 at about 1.4 astronomical units from the Sun, well outside Earth's track. That distance is not dramatic, but it is generous for safety and for for stable observations. The speed is high, yet the space between paths is higher. The crossing distance is large enough to rule out any impact. Compared with 1I Oumuamua, dust-poor and puzzling, and 2I Borisov, dust-rich and classic, 3I Atlas sat between, active early enough to invite spectroscopy. A simple plan followed: nightly photometry, moderate resolution spectra, coma and tail morphology, and orbit refinements. If the orbit already speaks truth, the green may tell us where it learned that language. We test hard. How far can we trace it? We set the baseline first. In the days after discovery, observers built a clean, color-neutral record of the comet's head and tail for later comparison. No enhancement, no stretching, just the coma, the stars, and the slow slide across the field. The first week was steady. Dust activity rose gently. Brightness ticked upward with rotation and viewing angle, but the green channel showed no advantage over red or blue. If a surge was coming, it had not arrived. Geometry helped. Phase angle widened. Elongation from the sun increased, peeling the comet out of glare and into usable twilight. New windows opened at dawn and dusk, brief but repeatable. The community organized. Shared calendars, standard filter sets, exposure ladders, and comparison stars set a common floor. Broad bands for context, narrow bands for proof. The rule was simple: measure, repeat, report. Late August broke the calm. The light curve rippled. Gas indicators rose. Teams shifted time toward moderate resolution spectra, hunting lines that would justify any claim of color. Then came the lunar eclipse. The sky darkened evenly. Airglow flattened. Background gradients fell. Long exposures and narrow band imaging showed an excess near the head that simple color stacks could not explain. Not the tail, not a smear, a local bloom around the nucleus. Replication mattered. A northern and a southern team reported the same behavior within hours, using different cameras, filters, and processing pipelines. The curves differed in detail but agreed in slope. Noise fought back. Flats, darks, and sky flats were applied. Saturation checks, gradient tests, star checks. One by one, false artifacts fell away. The log became a table. Instruments, filters, exposures, outcomes, with flags on the best repeats. If the bloom was narrow in time or angle, that was a clue. Which test runs first tomorrow? Green on a comet is not paint. It is a sentence written in light. Sunlight hits molecules near the nucleus and shakes them into glowing, not reflection, emission. Lines above the dusty continuum tell us which actors speak. Dust reflects sunlight broadly, but gas writes in sharp letters. Lines map identity, ratios beat impressions. The lead actor is diatomic carbon. Its Swan bands sit in the green near 4,770 angstroms and 5,165 angstroms. When these bands rise above the continuum, the coma looks green even if dust stays neutral. Where does diatomic carbon come from? Parent volatiles split under radiation. Acetylene and ethane are candidates. Carbon-rich grains can also feed fragments that pair into diatomic carbon. Fluorescence sends the energy back as narrow green light. Cyanogen adds a push. Its strong band lies near 3,880 angstroms, mostly in ultraviolet. It can absorb energy and pass the kick along so that green bands brighten even though eyes do not see ultraviolet directly. There is another suspect, the forbidden oxygen line near 5,577 angstroms. Sky glow and air glow carry it. The cure is sky sampling and a spectrum that resolves the oxygen line away from the Swan bands. Lifetime and motion sculpt the map. So diatomic carbon breaks quickly. Radiation and solar wind shear split gas and dust. Green piles up in the coma where molecules are born and die fast. The tail travels with survivors that do not glow in the same bands. The test is clear. Use narrowband filters for diatomic carbon and for CN, take resolution spectra. Compute the diatomic carbon to CN ratio. Subtract a clean sky. Compare with benchmarks like Comet 2022, E3Z-TF and 46P Wirtanen. If our visitor departs from those ratios, what parent chemistry hides inside? Spectroscopy frames the claim. The question is simple: Which lines rise above the dusty continuum, and by how much? If the green is real, diatomic carbon must declare itself, or a partner must. If the green is an artifact, lines will flatten into slope and noise. The setup is modest but strict. Resolution near 1000 to 3000. Slit aligned with the wind. Flux calibrated against nearby standard stars. Sky windows measured before and after the comet to catch airglow and gradients. Exposure ladders to trade signal for time. Early results hint, but do not seal. The Swan bands of diatomic carbon graze the noise floor, small humps over a neutral slope. Ratios are fragile under clouds and moonlight. Longer, darker nights are needed. CN remains elusive, but possible. A faint bump near the ultraviolet edge flickers with air mass. Some teams log a detection, others see only drift. For now, the line awaits repetition. The forbidden oxygen line at 5,577 angstroms sits like a trap. Sky glow carries it, and so can the instrument. Careful subtraction of sky frames and comparison with control fields keep the false green at bay. Dust sets the stage underneath. Teams fit the continuum and subtract it, checking that any residual is narrow and coherent across apertures. A red or blue tilt in dust can masquerade as color, fitting guards against the tilt. Aperture and seeing shape the picture. Spectra are extracted in rings around the nucleus to test how any line fades with radius and with time. True gas should decline differently than reflected dust. Cross-checks matter. North and south, different optics, different pipelines, the same thresholds. Agreement would make the claim breathe. Provisional reading. If diatomic carbon stays weak while CN appears, the parent mix may be unusual. If both stay weak, the green likely belongs to processing. Which outcome will tomorrow's clean spectrum choose? We estimate the nucleus by inference, not by sight. Absolute magnitude gives a starting brightness. Assumed reflectivity sets a scale. Yet coma light pollutes the core, so any diameter is a range, not a verdict. Dust has its own ruler. Observers measure AF-rho, a composite index tied to dust cross-section near the nucleus. It rises with activity. Watching AF-rho against time and heliocentric distance reveals whether the comet is steady, pulsing, or preparing a burst. Gas is counted by proxy. Lines from CN and from OH trace fragments of parent volatiles. With a Hazer-style model, teams convert a measured line flux into a production rate and then into a rough percent of the surface that must be venting to feed it. That active fraction rarely reaches unity. Instead, vents open by latitude and by hour. Topography shields some ice and celebrates other patches. Jets appear, precess, and fade as the nucleus rotates. Solar heating drives the tempo. Insolation rises as the comet drops inward. A shallow thermal skin depth means the day side bakes, the night side chills, and a rotating wave steers gas release. Peak activity often lags the moment of closest approach to the sun. The spin matters. Light curves mark dips and crests that hint at the period. If the body tumbles, patterns smear, but torque from jets can lengthen or shorten the clock. Tiny thrusts accumulate. Non-gravitational accelerations bend the path by milliseconds, and the same gas can twist the spin. Precision astrometry watches for both. Morphology follows physics. Coma breadth, tail opening angle, and grain sizes record the engine's state. A sudden outburst writes a sharper, wider fan. Heating can unlock parent molecules that feed diatomic carbon. When would that green bloom turn on, and for how long? Orbit sets the stage for every observation. Elements sketch a path, a high eccentricity above one, a steep inclination lifting the visitor above the ecliptic, an argument of perihelion that bends the arc, and a longitude of ascending node marking the plane crossing. Geometry is the metronome. Distance and speed set cadence too. Approach and departure matter. 3. Atlas descends from high northern sky, cuts the sun's plane, and leaves on a tilted southbound track. That slope compresses windows for some latitudes while expanding them for others, and it decides who sees the comet at a comfortable hour. Perihelion arrives in late October of 2025, near 1.4 astronomical units. As that date nears, angular motion quickens, then slackens after the turn. Short exposures reduce trailing near the peak. Longer exposures return once the rate calms. Phase angle controls how dust shines. Large phase angles amplify forward scattering and carve a dramatic fan, while small phase angles favor a compact head but suffer from glare. The trick is to choose nights where phase angle and darkness compromise. Elongation is the practical wall. As separation grows past 40 to 50 degrees, twilight yields more minutes. Morning and evening sessions lengthen and spectra become sane. Below that, the comet drowns. Apparent brightness starts with absolute magnitude and a slope law, but dust can rewrite both. Estimates carry margins. Sky quality often matters more than any forecast. The moon, altitude, and air mass edit every plan. Avoid the full moon. Aim for elevations above 20 degrees. Thin air helps the green. Filters and field of view influence success. Use broadband to center and narrowband to test lines. Frame wide enough to hold tail and comparison stars. Globally, latitude bands trade off. Northern teams hand to southern teams. When do the teeth of this key align for the clearest green, and who stands where they fit best? 3 interstellar visits teach different lessons. 1 Oumuamua arrived first, faint and fast, with a path that never closed. 2 Borisov followed, brighter and classic, its coma and tail obvious. Now 3 Atlas arrives on a hyperbolic arc, asking in green. Activity sets the tone. Oumuamua gave little dust and almost no detectable gas, starving spectrographs. Borisov gushed both, filling frames with grains and lines. 3 Atlas sits between, active enough to sample but not so bright that dust smothers every signature. Spectra tell sharper stories. Oumuamua offered no clear molecular bands, only a reddish slope. Borisov displayed diatomic carbon and CN cleanly, the usual comet chemistry. 3 Atlas runs narrowband tests now. If diatomic carbon rises above dust, the green becomes a measurement, not a mood. Shapes matter. Oumuamua lacked a normal coma and tail, perhaps a shard, processed ice venting invisible gas. Borisov was textbook, fan and ion streak aligned with the wind. 3 Atlas shows a compact head where color concentrates. Phase angle and trailing can exaggerate or hide it. Motion distinguishes them as well. Oumuamua's track hinted at non-gravitational acceleration. Borisov behaved by the book. 3 Atlas remains under watch for tiny jet thrusts. Sizes and reflectivity diverge. Oumuamua likely small and elongated. Borisov kilometer scale. 3 Atlas uncertain. Spin complicates light. Oumuamua probably tumbled. Borisov spun steadily. 3 Atlas is revealing a period through small rises and dips, the pattern still settling. Material history is the prize. If verified, green points to parent chemistry and processing in another system's nursery. Fieldcraft has improved. Shared calendars, identical reductions, cross-hemisphere replication. If 3 Atlas refuses both precedents, we face a rarer class. Time will test that claim. Which single measurement settles the case first? Start with the sky. Choose a night far from cities, dry air and a steady jet stream. Favor large elongation from the sun, or the even field of a lunar eclipse. Tools are straightforward, a fast lens or a small to medium telescope, a cooled camera if possible, a rigid mount. An auto-guider that keeps drift below a fraction of a pixel. Focus with a Bahtinov mask, then lock it. Calibrate before beauty. Shoot dark frames, flat frames, and offset frames. Dither between exposures to break-fix pattern noise. Keep the sensor linear. Do not saturate the bright core or comparison stars. Exposure is a bargain with motion. Short subs prevent smearing. Many stacks reclaim depth. Track at the comet's rate when testing its head. Track at the sidereal rate when measuring stars and background. Align 2 ways. First, stack on stars to preserve the field. Second, stack on the comet to isolate the coma. Compare the two. Look for green excess that hangs on the comet frame, but not the star frame. Filters decide tests. Broadband helps aim and context. Narrowband frames near the Swan bands of diatomic carbon and near the CN band test emission. Place comparison stars in every frame. White balance is not a vibe. Match a G2V standard star. Check catalog color indices. Keep the curve honest. Gradients cheat. Model the background with a low polynomial. Measure sky patches. Watch for airglow and urban light. Use sky flats when you can. Share raw data. Process independently. Compare flux curves across teams and hemispheres. Real signals survive new hands. The rule for trust is simple. If narrowband stacks aligned on the comet show a stable excess centered on the head, across nights and cameras, color becomes chemistry. Which frame will seal it tonight? Suppose the Swan bands of diatomic carbon refuse to rise above the dust. The claim of green still needs an answer. The investigator maps forks and cuts branches with tests, not sentiment. One branch argues for cyanogen. If CN dominates while diatomic carbon lags, ultraviolet pumping can brighten the green indirectly. The signal should peak close to the nucleus, then fade with radius faster than dust. The decisive check is a ratio of diatomic carbon to CN in concentric apertures tracked over hours. Another branch points to a stranger hydrocarbon chain. Radicals like C3, CH, and CH2 can contribute bands that mimic a tilt. Deeper spectra at the ultraviolet fringe will show whether an unseen parent drives a cascade into the visible. A third branch warns of forbidden oxygen at 5,577 angstroms and a neighbor at 5,632 angstroms. Sky glow and instruments carry them. Narrow lines that breathe with the night sky, not with the comet, mark the trap. Dust can deceive. White balance, a sensor's color matrix, and curve stretching create artificial green. Reference stars fix those, control fields fix the rest. Ion tails bring their own blue. Carbon monoxide ions and water group ions rarely land in green, yet leakage through filters must be ruled out by true narrowband work. Short outbursts complicate everything. A brief vent can spill rare parents for an hour, then seal. Only time-resolved light curves and back-to-back spectra will catch the switch. Atmosphere and geometry finish the list. Phase angle, airglow, aurora, thin cloud, and gradients impersonate color. Sky windows and multiple backgrounds expose the imposters. A simple decision tree follows. If diatomic carbon stays low while CN is strong, cyanogen leads. If both are weak, processing likely rules. If oxygen lines sharpen, the sky speaks clearly. What measurement tears away the disguise first? Interstellar visitors are not only messages, they can be cargo. The planet seed hypothesis says bodies from other suns cross young disks, shed dust and ice, and leave nuclei that help grains stick. A brief crossing can seed a future world. The outline is simple, the details fierce. Speed is high, yet gas in a disk can slow a traveler to a soft graze. That graze scrapes organics and ices and mixes them with silicates. Where nothing held together, a seed forms. Composition sets leverage. Refractory grains supply structure. Ices rich in carbon carry chemistry. Some seeds may carry unusual isotope ratios, metallic flecks of iron, and silicates that never met a furnace. Capture needs windows. Gas drag shears momentum. Across long spans, rare encounters add mass and complexity. Our first two interstellar guests sketch the spectrum. One eye, Oumuamua, hid its breath. 2i, Borisov, announced a classic coma. 3i, Atlas can extend the line if its green proves chemical. If diatomic carbon and CN rise together, we glimpse a parent mix from another nursery. Models and experiments show how dust in gas can stick in collisions. Threshold energy decides whether grains fuse, bounce, or shatter. Surfaces catalyze, ice films glue, porosity turns violence into union. The payoff is practical. A surplus of organics, metals, and catalytic surfaces tilts the odds for planet formation where stock is poor. Seeds do not make planets alone, they bias the ledger. Risks remain. Excess speed ricochets the traveler. Disks can be too hot or too thin. Observation is hard. Proof may be indirect. What could 3i Atlas add? Spectra, grain sizes, the ratio of diatomic carbon to CN, and light curves versus distance map cargo precisely. Which measurement should we book first to catch the act of sowing? Priority number 1 is light split into lines. Watch the Swan bands of diatomic carbon near 4,770 angstroms and 5,165 angstroms. Watch the band of CN near 3,880 angstroms. Confirm that lines rise above a fitted dust continuum and repeat across nights. Keep a steady photometric drumbeat. Build light curves in green filters and in neutral bands. Sample at regular minutes. Track rises and dips that mark rotation. Log any short spike and mark the time for follow-up spectra. Fix apertures by radius. Hold the same physical scale around the nucleus when the comet grows or shrinks. Measure the ratio of diatomic carbon to CN at several radii. True gas fades with distance differently than reflected dust. Ratios that change with radius tell a cleaner story than single fluxes. Add polarimetry. Linear polarization traces grain size and porosity. Compare the degree of polarization with any growth in diatomic carbon. If gas rises while polarization falls, a chemistry bloom may be riding over steady dust. Tail shape is a witness. Note the opening angle, any curvature, and any thin ion streak. Compare on nights with similar phase angle. Separate dust fans from gas features by motion and by persistence. Calibration is not optional. Dark frames, flat frames, and reference stars of type G2V hold the color scale steady. Avoid saturation. Map sky gradients. Test for the forbidden oxygen line near 5,577 angstroms and remove it if present. Demand independent confirmation, north and south, different optics, different pipelines. Set a minimum signal to noise of 3 for each claimed line. When all of that is in hand, decide. The rule is simple. If narrow lines persist and the ratios hold, declare green as chemistry. If not, withdraw the claim. One night to spend. Which single test wins the hour? Headlines love panic. A green comet, a far guest, and a clock become a promise of impact. That is not what the numbers say. Images in feeds are not evidence. Artistic renders stretch color, long exposures smear motion, white balance tilts the palette. Real data begin with calibration frames, reference stars, and spectra showing narrow lines above a dust continuum. Orbit decides safety. 3I. Atlas rides a hyperbolic path with eccentricity above 1 and a minimum orbit crossing distance. It will not hit Earth. High speed does not change that. Distance is destiny. Green is not a warning light. It is molecular emission in the coma near the nucleus, often from diatomic carbon. It is not a toxic plume, not radiation, and not a coded signal. It is sunlight shaken into lines. Sizes and speeds in posts often inflate drama. Convert units, respect scale. An object millions of kilometers away will not suddenly change course into a bullseye. Brightness forecasts are guesses, and the human eye is conservative in the dark. Beware false links. Earthquakes, auroras, and storms do not answer to comets. Coincidence is not causation. Safety is practical. Observe from dark sites. Avoid lasers and searchlights. Do not trespass. Shield your screens. Let your eyes adapt. Share the sky, not the scare. If you need truth, check ephemerides, independent observing groups, and spectra. Ask 4 things. Are lines repeated across nights, across instruments, across apertures, and above dust? There is no doomsday here. So what is worth your excitement, and where should we point the glass tomorrow? We close the loop without closing eyes. A green claim became a plan. Images, spectra, and light curves pried rumor from result. We put impressions last and repetition first. Break the hypothesis, keep the evidence. That is the order. Chemistry is the hinge. If diatomic carbon stands up, we have the source for the glow. If it does not, cyanogen and stranger parents wait their turn. Either way, the color points to birthplaces and histories of heat and ice. Interstellar matters, cargo matters. Planet seeds are not poetry. Dust, ice, organics, and metals change destinies when they cross a disk. 3I Atlas could add a grain to the ledger, a line to the story. Method wins trust. Independent teams, shared stars for color. Oxygen at 5,577 angstroms subtracted clean. Claim rules written before night begins. Data shared when night ends. Operations stay sharp. Pick geometry, not luck. Reserve dark time near large elongation. Trade cadence for depth when rotation whispers. Post files. Invite a pair of hands. Outcomes reduced to 3. A. Diatomic carbon confirmed. B. Cyanogen leads. C. Processing fades the green. Each path carries a next step. Deeper spectra, longer baselines, tighter ratios. Decision lines are simple. Lines above dust with signal to noise over 3 and ratios across radii mean go. Anything less means wait. Say what you know, say what you do not. This is not a threat, it is a frontier. A third voice from other stars has spoken. If the door opens, what will we see first tonight?